Okay, so maybe we'll get started. So we're happy this week to have Shaosai Huang from Wisconsin-Madison, and he's going to talk about topological rigidity of the first Betti numbers and Ricci flow smoothing. Go ahead.
Okay, first, it's great to see you guys in Toronto. I'm from Toronto and I want to go back, but because of this pandemic, I cannot anyway. And also thanks for Spiral for the invitation. Okay. So today I'm going to talk about the topological rigidity of the first Betti numbers and Ricci flow smoothing. So basically here, this Ricci flow smoothing is the techniques that we employ to prove this so-called topological rigidity theorem. And this is a joint work with Bing Wang in last year. Okay, so our story starts from Gromov's almost finite manifold theorem. That's a theorem proved in the 70s by Gromov and later improved by Hu in 1982. So that theorem claims that there's a dimensional constant epsilon n, which is positive but very small, such that if a closed n-dimensional Riemannian manifold, MT, satisfies this diameter and curvature condition, namely the diameter squared times the maximum of the sectional curvature is small enough, which is characterized by less than epsilon squared, then M is diffeomorphic to an almost flat manifold. So to understand the content, we basically will briefly talk about what is an almost flat manifold. Roughly speaking, an almost flat manifold, which is also known as a infranil manifold, is by definition the quotient of a simply connected nilpotent Lie group N by a discrete subgroup of the affine transformation group of that nilpotent Lie group. And this subgroup is has a finite index lattice subgroup from the translation. Okay. So this uniform bound of the index here is part of the Gromov's theorem. So this theorem is sort of striking upon its appearance because if we look back the assumption, it is very simple. It's just some metric conditions. It's diameter and sectional curvature, satisfying some inequality. So that's just curvature, and diameter conditions. But then it tells the diffeomorphism type of the manifold. So that's kind of surprising upon its appearance. This theorem becomes even more important as we study the collapsing of Riemannian manifolds with bounded sectional curvature, because they serve as this almost flat manifold serves as the very small collapsing fibers, and that's something we're going to talk about later. Okay. So if we talk about the collapsing of Riemannian manifolds, then we want to basically refer to certain moduli spaces of Riemannian manifolds. Here, the first one we are going to talk about is the M Riemannian ND. This is the notation here. That denotes the collection of n-dimensional Riemannian manifolds with sectional curvature bounded between positive and negative 1, and the diameter bounded above by some uniform constant, let's say d greater than 1. So that's the collection of Riemannian manifolds. Another collection of Riemannian manifolds is this M Riemannian NdV. That's a subcollection of this MND, and it's a collection of Riemannian manifolds such that besides the curvature and diameter conditions assumed, we also assume that the volume of these compact manifolds are bounded below by V. So this is a submoduli space out there. Actually, here this N should be any, let's say K less than or equal to N, any lower dimensional. An extra moduli space is M Ricci N. It denotes the collection of Riemannian manifolds, which are n-dimensional, and satisfies this Ricci curvature bounded below by n-1. So obviously, this M Ricci N is a much larger moduli space than this M Riemannian ND. Okay. So we will equip this Riemannian manifold, moduli spaces, because Riemannian manifolds are metric spaces to begin with. So we will equip this moduli spaces the pointed Gromov-Hausdorff topology. Of course, in the first two cases, we only need to consider the Gromov-Hausdorff topology because they're just compact spaces. And by Gromov's compactness theorem, these moduli spaces are pre-compact in the Gromov-Hausdorff topology. Namely, if you consider a sequence of elements in any of these moduli spaces, a priori you get a sequence. You get a subsequence that converges to a metric space. But because we have this very strong curvature conditions, like in the first two cases, we have the sectional curvature bounded in between -1 and 1. In the third case, we have Ricci curvature lower bound. So we expect that although by Gromov's theorem, we have a compact metric space as limits, but we expect actually better structure of the metric limit space. And also we expect better regularity of convergence or better topology, not just the Gromov-Hausdorff topology. So you can think of Gromov-Hausdorff topology as, say, like L infinity convergence of functions, but the functions is not, it's actually for manifolds. But because of these curvature conditions, we expect better topology. We can improve the convergence. So here we come to this triggers finiteness theorem. Basically, we know that this moduli space of M Riemannian ND is sort of a very large moduli space because you only have the curvature bounds and the diameter bounds. But for any dimension less or equal to n, this M Riemannian KdV, remember we add an extra volume lower bound condition, is actually very small. So that's the triggers finiteness theorem in the 1970s. It says that the moduli space M Riemannian KdV has only finite diffeomorphism types. And the Gromov-Hausdorff topology on this moduli space is also the same as the C1 alpha topology, so C1 1/2 topology. So this C1 1/2 topology means, so this 1/2 is just arbitrarily chosen constant in between 0 and 1. Okay, so we will elaborate more on this topology a little bit. We see this topology as the following. See if, or the content of this theorem basically says the following. If Mi is a sequence of Riemannian manifolds in this moduli space M Riemannian KdV, and Mi converges to some metric space in the Gromov-Hausdorff sense, and the existence of such metric space is guaranteed by Gromov's compactness theorem, then in actuality, this a priori very rough limit metric space is actually an element of the moduli space. It's actually a smooth Riemannian manifold. And also the convergence topology can be improved to the so-called C1 1/2 trivial Gromov sense. Namely, we have diffeomorphisms from the Mi to Xi to the limit Riemannian manifold Xi X, so that the push forward of the metric which is the pullback of the inverse diffeomorphism, those metric as tensor fields on X converge in the C1 1/2 topology to this limit metric tensor. And therefore, it's a very so it's like starting from this L infinity topology convergence to C1 alpha convergence in the, say, like in function theory. Mm-hmm. So that's triggers finiteness theorem. But
so
it also
can I ask a question? So for any positive V, this is finite.
Yeah, of course, given the diameter bound and the curvature bound, you have an upper bound of the volume. Right. It's not any V. Yeah, there's some say like determined by the diameter and the dimension and the curvature. There's a upper bound of the V.
Right, but if you do the union as V goes to 0, then it's definitely infinite for sure, or we don't know.
So the thing is, I want to say that there's a small V that's lower bound. I want this V to be uniformly lower bounded. That's unhabitable. Yeah.
But I mean, if you look at these spaces and you have a sequence of V's going to 0, mm-hmm. and you take the union of those, is it going to be definitely?
That's a good question. That's the thing we're going to deal with.
Okay.
So if we do not have a zero bound of the V, then a priori they don't have this finiteness theorem.
Right.
Yeah, and that's actually the exact thing we're going to deal with.
Okay.
Because you may notice that this M and D can be thought of as, say, take V as the rational and take the union of the V's. Yeah. Okay, so Triggers finiteness theorem, besides this being like a nice theorem, it tells that the moduli space is pretty small. You only have finite diffeomorphism classes. So in our mind, we can think of this moduli space, M Riemannian KdV, as a sort of minimum models. Any manifold in that moduli space can be think of one of the minimum models for manifolds in this larger moduli space. But what is the connection between an arbitrary space, an arbitrary manifold in this larger moduli space and one of the minimum models? What is the connection here? So that's the question. How can we relate a generic element in this larger moduli space to one of the minimum models in this smaller moduli space? And that's Fukaya's theorem. So Fukaya in 1987 proved the fiber-bundle theorem, which says that given the diameter D and given V, these are the two parameters. Again, V is potentially very small, but it's a uniform thing. There's some epsilon depending on the dimension and this small volume V, such that if I get a manifold in this general, a larger moduli space, and I get N as one of the minimum models in lower dimension, and suppose that M if you look at to the naked eye, it's very close to the lower dimensional manifold N. Then there's a surjective C1 map F from M to N, which is an almost Riemannian submersion. So you see that actually M is a fiber bundle over N. See, so the thing here is that N has this volume lower bound, maybe lower dimensional, but has this volume lower bound. But M, we do not have any volume lower bound requirement. If M happens to be very close in the L infinity sense or Gromov-Hausdorff sense to M to the lower dimensional minimum model, then it has to be a fiber bundle over that. So that's Fakaya's fiber bundle theorem. And moreover, the fiber of this fibration or the fiber bundle are diffeomorphic to almost flat manifolds. That's what we said that Gromov's almost flat manifold theorem becomes very important in the study of the collapsing geometry. So here we see that M collapses to N because the dimension of N is strictly less than the dimension of M. In this application, and M looks because of the Gromov-Hausdorff proximity of M and N. M looks to the naked eyes like a lower dimensional manifold, but actually it is higher dimensional one. So here basically it resembles a similar feature as Gromov's theorem by the fact that it's purely the metric condition, this Gromov-Hausdorff closeness, and the curvature condition that determines the topology of them, basically. Because roughly speaking, we know that the collection of all minimum models, like all the N's, there are only finite many of them. So basically, we have the knowledge in mind already. Or we have all this manifold in our list. But then M cannot be too complicated over N. It has to be a fiber bundle over that. Of course, you need to encode this fiber bundle structure, but the fiber structure is clear, and the fiber is only the fiber bundle structure. So basically, you determine the topological type of M. Diffeomorphism type of M. So this theorem provides the basic picture of the collapsing geometry with bounded sectional curvature. And so basically the whole theory of collapsing with bounded sectional curvature is like you get the higher, or the collapsing manifold is an infranil fiber bundle over some lower dimensional orbifold with corners. So basically infranil fiber bundle is just nothing but a fiber bundle whose fibers are quotients of almost flat manifolds. And this orbifold with corners basically means that locally it is like Euclidean space quotient by an isometry group action, but this group has its identity component as the torus. Yeah, so this is just a rough recall. So this collapsing geometry with bounded sectional curvature is in a very well-developed stage. Although there are many questions left, of course, but the basic, the fundamental theory has been laid down by Chigar, Fakaya, and Gromov, and also their students, Xiuxiong Chen. Okay, but now the question is, we're in the 21st century, so the question is collapsing geometry with Ricci curvature bounded below, not just the sectional curvature, because that's very restrictive. Okay. So the question is, how about the collapsing geometry of manifolds with Ricci curvature conditions, such as the collapsing of Ricci flows? As the Ricci flow evolves, it possibly collapses, and the elements, the collapsing of elements in M Ricci N. So the collection of manifold with Ricci curvature lower bound. So why do we care about it? Because first, that's our instinct. Because as mathematicians, you want to generalize. You want to find weaker curvature conditions. You want to have, it's more natural setting. You can think of it as it. But the second motivation, I guess, is much more serious. It's from mathematical physics. It's the SYZ conjecture in mirror symmetry. In its most original version, it considers about this collapsing of Calabi L3 folds, and it expects that a family of Calabi L3 folds, if they degenerates, it's going to be there's going to be a singular fibration over S3, homeomorphic S3, and the generic fibers are torus. So that's the basic expectation. And one more motivation in Kähler geometry or algebraic geometry, there's the abundance conjecture. It's something like it's still really. It has a it's major part of the minimum model program. So basically, you can rephrase the abundance conjecture in Kähler geometry as understanding the long time behavior of the rescaled Kähler or the normalized Kähler-Ricci flow starting from NAF initial data. So what's your expectation is as the flow evolves, maybe basically your expectation is, so this NAF initial data is actually semi-ample. So basically, if there's some fibration over there's some singular fibration over a single base. Okay, so the general expectation in all this collapsing issue is that there's going to be a singular fibration structure over a singular base. So basically speaking, compared to this original collapsing geometry with bounded sectional curvature, it's like the singularity is very well understood in this collapsing with bounded sectional curvature case. And in this general case, in this collapsing with Ricci curvature condition case, basically, so like in this motivation 2 and 3, basically we will have, like in this motivation 2, we will have torus fibers, and in this motivation 3, basically we will have Calabi-Yau fibers. So it's like more complicated fibers and much more complicated singularity behavior that we don't understand. Whereas in the classical collapsing with bounded sectional curvature, the singularity structure is very well understood. Yeah. Okay, now, so where do we get started? Basically, remember that it was Gromov's first discovery of the almost finite manifold theorem that resulted in this development of collapsing with bounded sectional curvature. So basically, a first instinct is to ask whether there's a generalization of Gromov's almost finite manifold theorem to the Ricci curvature bounded case. So that's one attempt by Xianzhe Dai, Guofeng Wei, and Rugang Ye in 1996. So they attempt to generalize Gromov's almost flat manifold theorem to the setting of almost Ricci flat manifolds. Basically, their theorem says that there's a dimensional constant epsilon, which is again positive and small, such that if a closed n-dimensional Riemannian manifold with conjugate radius bounded below by 1 satisfies this condition. So this condition reads that the diameter squared times the maximum of the Ricci curvature in its norm is very small, characterized by less than epsilon squared. Then M is diffeomorphic to an almost flat manifold. So basically here, indeed, if you only look at this curvature diameter condition, it significantly weakened Gromov's assumption. You basically replace this sectional curvature uniform bound by this Ricci curvature norm. But here they need to assume this conjugate radius uniformly lower bounded by 1, and it's a very strong assumption, and it is it is almost impossible to check pointwise. Yeah, so they indeed generalize Gromov's theorem, but they assume something that's really strong and not that realistic. But here, their techniques of proof relies on the so-called Ricci flow smoothing technique, and that is the major technique that that in my work with Bing Wang that we deepened and utilized. And they're like this condition, diameter squared times the maximum Ricci curvature norm is more. It's not restrictive. I mean, you can put some other assumptions, like Professor Kapovich recently assumed the very small positive bound of sectional curvature and a almost non-negative lower bound of the Baker-Emery-Ricci curvature tensor. So it's like another set of different almost flatness conditions. Okay, but in any of these generalizations, they roughly need to assume certain sort of sectional curvature upper bound, which is something we don't want to make use of in the Ricci curvature collapsing setting. Like sits here, this conjugate radius lower bound is actually a major consequence of this sectional curvature upper bound. And in Kapovich's condition, he directly assumed this very small positive upper bound of the sectional curvature. So although these are generalizations of the theorem with the Ricci curvature back in their mind, it's still not so applicable. It's not, yeah, they're nice theorems. But I think a more natural thing is the so-called Coding-Gromov's theorem. This theorem was result was conjectured by Gromov in the 1970s and was proved by Coding in 1997 in his annals paper. So the theorem says that there's a dimensional constant, positive very small, such that if a closed n-dimensional Riemannian manifold satisfies this almost non-negative Ricci curvature. So very nice thing here is that there's no curvature upper bound assumed here, just non-negative Ricci curvature, almost non-negative Ricci curvature. And and the first Betti number of the manifold is actually equal to the dimension. So it's like the maximum possible first Betti number. Then M is diffeomorphic to a flat torus. So the beauty of this theorem is that it replaces this upper bound of the sectional curvature by this very natural topological condition. It's numerical and natural. So that's the beauty of this theorem. But this theorem is not so unexpected because we all know the Bochner's technique. We know that if it's not this negative upper bound, but greater than or equal to 0, then this theorem is like proved in 1950s or 60s by Bochner. It's very classical. So therefore, we can think of Coding's theorem as a quantitative version of Bochner's theorem. So there's like a quantitative gap between 0 and some negative thing. Yeah. Or it can be think of as the quantitative version of the Chigall-Remorse splitting theorem, because Bochner's original theorem can also be proved by considering everything on the universal covering space. Yeah, so it's also a quantitative version of the Chigall-Remorse splitting theorem. And of course, a historical remark is that the diffeomorphism version is actually proved by Chigall and Coding in their JDG paper. And of course, they had many JDG papers. They used the Riefenberg method. And Coding's original proof only was about this homomorphism. It's not diffeomorphism. Okay. All right, now it comes to the theorem that I want to present. It is the joint work with Bing Wang last year. And our theorem says that given the diameter D and volume V, just like in Fukai's fiber bundle theorem, he assumed that there's some parameters. Then there's a constant epsilon depending on this N and D and V, such that if I have a Riemannian manifold in this larger moduli space, in the Ricci moduli space, and one of the minimal models, and if they are very close, again, to the naked eye, in the Gromov-Hausdorff sense, then we have an inequality about the first Betti numbers. So this first Betti number difference of the high dimensional manifold and the low dimensional manifold is bounded above by the dimensional difference. Moreover, if the equality holds, then M actually is diffeomorphic to a fiber bundle, a torus bundle over N. So this difference of the Betti number is exactly complemented by the N minus K loops of the fiber. So that's our theorem. Let me give some comments. We think this theorem is parallel to Fukai's fiber bundle theorem. So basically, it's like Gromov's almost flat manifold theorem describes the collapsing fibers of Fukai's fiber bundle theorem, and here our theorem coding Gromov gap theorem describes the collapsing fiber of our theorem, and our condition is similar, because let me just say, we can see that M and N are very close, and the fiber is very small. The fiber is of size epsilon. But suppose we also have a uniform Ricci curvature lower bound, then the diameter of the fiber times the Ricci curvature is almost non-negative. And that exactly fits into coding Gromov gap theorem. And also we have like the fiber has Betti number exactly equal to dimensional difference. So basically we have a parameterized version of coding Gromov gap theorem. And in fact, if we notice that, suppose we know that M is an N minus K torus bundle over N, and N is aspherical, then we can write down a long exact homotopic sequence. And then we can tell actually that the difference of the first Betti numbers is equal to the dimensional difference. So our theorem basically tells the inverse. Therefore, we call it a topological rigidity, because you know something about the first Betti numbers, and then you can tell the diffeomorphism type of the manifold.
Sorry, can you remind me what aspherical means? It means the higher homotopy groups are...
Yeah, so like pi 2 and above are all 0.
I see. Okay, that's what
pi 2 and pi 3 and etc. are all 0. Yeah. So our proof is also based on the Ricci flow smoothing technique. And actually later we continued our work. We were able to localize the Ricci flow smoothing technique. So basically, you notice that here in the theorem, we need to require that M is a closed manifold, and we need to require that the whole manifold is close to a lower dimensional smooth manifold. But we were able to localize that result. So to say that, say if I have a neighborhood in the manifolds that's close to a lower dimensional limit, then we can prove a similar fiber bundle theorem. And also the collapsing limit may not be a smooth manifold. Here, a critical thing is that this collapsing limit M is close to N and N is smooth manifold. That's very important for us. But we're later able to generalize that, say, if the collapsing limit is an orbifold, I mean, actually an orbifold neighborhood, then with certain topological conditions, we can basically show that it's a fiber bundle still. Yeah. And also in a forthcoming work, a joint work with Xiuxiong, we will show that. So this fiber bundle theorem is non-trivial only when the Ricci curvature is sufficiently negative. If the Ricci curvature, if everything is satisfied as the theorem we just proved, and we just stated, and if the Ricci curvature is almost non-negative, then M has to be a trivial bundle over N. Then M is actually diffeomorphic to the product of N and the torus. So here, basically, if Ricci curvature of M is non-negative, then it is homeomorphic to a product of the torus and N. But actually, we have a certain gap here. So that's in the forthcoming work. All right, I guess I'm halfway. So let's get into the proof of this theorem. Any questions so far? Okay, maybe I'll continue with this major techniques. So this major technique is basically I will. So the thing here is, yeah, maybe I will first talk about the Ricci flow smoothing, and then I will talk about basic strategy. So Ricci flow is a certain geometric flow introduced by Richard Hamilton in 1982. And suppose M is a smooth closed Riemannian manifold, then there's a family of smooth Riemannian metric that's whose initial value is the given Riemannian metric, such that they solve this partial differential equation. The time evolution of the metric of the Riemannian metric is equal to -2 times the Ricci tensor. Basically, with this technique, Hamilton showed in 1982 that this flow exists for a short time. I mean, basically, he showed that if we start on a closed manifold, we can start the Ricci flow. And Wang Shi in 1989 generalized Hamilton's result to complete manifold. Hamilton only dealt with closed manifold, and later Shi showed a similar result for complete manifold with the condition that the Riemannian curvature is uniformly bounded. Okay. Just a second. Yeah. So our basic strategy of this of proving this theorem is the following. Basically, we know that the Riemannian manifold to begin with has only Ricci curvature lower bound. It's smooth, but we don't have any uniform control. So what we want to do is that we want to start a Ricci flow with this initial data mg. So give me the Riemannian manifold, I start the Ricci flow. It's closed. Therefore, by Hamilton's result, we can start the Ricci flow. By Shi's result, the evolved metric have better regularity. It has this control. This has this uniform control on the sectional curvature. Therefore, it gives our hope that, well, if this evolved metric with better regularity is still very collapsing, namely in the sense that it's still Gromov-Hausdorff close to the lower dimensional Riemannian manifold, and then we can just refer back to the classical theorem of Kaya, and we're done. So that's the basic idea here. But yeah, so we can go back. That's what I just said. Yeah. However, there's one essential problem, namely in Shi's estimate, the curvature bound is 1/t. So that's, of course, that's the nature of all heat flow smoothing. Therefore, we have two problems. Namely, if the T, we do not have any uniform existence time of the flow. So T does not have any uniform lower bound, then the curvature can be absolutely bad, actually, essentially no control. So Shi's estimate, although it looks good, without any uniform control, it's nothing. It gives us nothing. Yeah, so the key difficulty here is to obtain the Ricci flow existence, is to obtain a Ricci flow existence time lower bound, uniformly depending on the given information, namely the Ricci curvature lower bound, the collapse into a dimensional minimum model, namely the Gromov-Hausdorff distance, and the Betti number condition. So we want to obtain this uniform existence time lower bound only depending on this data. So basically, the basic theorem we're going to rely on is the pseudo-locality theorem of Ricci flow. That's proved by Perelman in 2002 in his first famous paper. And I mean, he has made more famous. I mean, he also has famous people before that work, but in his striking work, you know. And then another condition was proved by Tian Wang. Their proof is like following the basic ideas or basic strategy of Perelman's, but we need to prove with a different set of conditions. The first set of conditions is this one. Maybe let me state the theorem. So for any small parameter alpha, there's a positive constant, epsilon p and delta p. So this is the constant that characterizes how the initial data is locally look like Euclidean space. So that if mg is a Ricci flow solution defined for some certain amount of time, with each time slice being a complete Riemannian manifold, if one of the conditions holds for a point p. So the first condition is Perelman's condition. It assumes that on the unit geodesic ball around the point in the initial manifold, in the initial data, this initial scalar curvature is bounded below by 1. And the isoperimetric constant of this domain of this unit geodesic ball is almost the Euclidean, almost isoperimetric constant. It's greater than 1 minus delta p. This delta p is this closeness to this Euclidean isoperimetric constant. Sorry, here I should write IM. It's IN. It's n-dimensional Euclidean isoperimetric constant. Or another set of conditions. These two set of conditions are actually they're sort of equivalent, but on its statement they're independent. Or if we assume Tian Wang's condition, namely instead of scalar curvature, I assume this Ricci curvature lower bound. Ricci curvature almost non-negative, and the volume of that geodesic ball is almost equal to the Euclidean ball. So these are two sets of independent conditions. If either of these conditions for the initial geodesic unit ball around the point P is satisfied, then we have this curvature bound. So basically, then for any time up to a certain period of time, this Riemannian curvature has uniform bound. I mean, still here, we have this 1/t type of curvature bound, but we know that this bound is up to this uniform constant epsilon p squared. Therefore, we can just evolve the metric up to this uniform time, and here we obtain, although a very bad, but uniform curvature bound. So here, the uniformity is the key thing. Okay, so here, this is uniform. Because as you may see, it only depends on the dimension and this parameter alpha. Okay, so basically, if we can apply the pseudo-locality theorem, then it will give us a definite uniform existence time of the Ricci flow. Any questions?
So I guess I don't quite understand why you're saying it's uniform. So it does still blow up as t goes to 0, right? So how
right. So we see that if the existence time is larger, then this bonding improves, right? If t is say 1,000, that's better than when t is very small, right?
Yeah, but only when t is close to that, right? No, yeah, okay. So I see I see. Okay.
Only when t is. So my point here is that this existence time can be bounded below by this epsilon p squared.
I see.
Therefore, the flow exists at least for the period of epsilon p squared. Okay. And so you can the metric the smoothing metric you use to replace the original metric is this g at time t equals to epsilon p squared. And this epsilon p squared is a uniform thing.
Okay.
And therefore the uniformity of this bound.
Thanks.
All right, another thing is that, well, if I replace the metric with another metric, is this metric still very close or sufficiently close to this collapsing metric? right? So I replace it with another metric with better regularity, but this metric may fail to satisfy the Gromov-Hausdorff condition. So here we need to rely on this distance distortion estimate, which is proved by Xiuxiong Chen and his collaborators, a bunch of collaborators. So basically, his theorem says that suppose Mg is a smooth Ricci flow, satisfies a first condition, namely Ricci curvature is bounded below, and this volume of the unit geodesic ball is always bounded below. And the second is that in the space-time, there's a curvature bound by this 1/t. Then for any points on the manifold whose distance are up to the square root of t, we can compare the original metric and the evolved metric, and they're small. The difference is small, roughly speaking. So this is a pretty technical lemma. We just stated here for the completeness. Basically, it says that if we have initial data sort of non-collapsing and Ricci curvature lower bound, so this Ricci curvature lower bound is natural, but non-collapsing, we don't have it. And also the space-time curvature bound, then we can compare the initial distance function and the new distance function, the evolved distance function. Therefore, if this initial metric collapses, this evolved metric also collapses. Okay.
What does the vertical bar mean in the psi d of alpha?
So basically, V, that means V is a parameter that determines this constant, but V is fixed, whereas alpha is another parameter that determines this constant. But as alpha approaches 0, this psi goes to 0.
I see.
Yeah, basically we're gonna take alpha to be very, very small.
Okay.
And this alpha, remember, comes from Perelman's theorem. Here, I have an extra parameter alpha here. Yeah. So basically, we want to apply this distance distortion estimate as well as Perelman's pseudo-locality theorem for our purpose. However, we notice that there's this essential condition, namely this volume lower bound, or similarly here, this volume lower bound. You have to require this initial data to, in the volume sense, it's like almost Euclidean, in order to apply this theorem or this distance distortion estimate here. Actually, this is the only, on the other hand, and this is the only thing that we really need to worry about, because once this initial volume condition is satisfied, then Perelman's theorem gives you the desired curvature, space-time curvature bound, which is exactly of this type. And this second condition of this distance distortion estimate is automatically satisfied. So what we really need to worry about is this non-collapsing initial volume. Yeah, so the space-time bound curvature bound is natural. So here, the uniform estimate depends on the volume lower bound of the initial data. And that's the same issue for applying the pseudo-locality theorem. Because in our case, the initial data cannot look, given any small neighborhood, not absolutely small, given a certain size, the neighborhood does not look like n-dimensional Euclidean space because it collapses to low dimensional manifold. It looks like lower dimensional space. So this condition cannot be satisfied. And that's the major difficulty that we need to overcome. Yeah, so in our situation, the m-dimensional manifold, which is n-dimensional, higher dimension, is very collapsed. It looks like lower dimensional one. So the locally un-Euclidean condition may drastically fail. So while we can start the Ricci flow on M by Hamilton's result because M is compact, this possible collapsing may destroy any uniform estimate about this existence time, because priority we cannot apply theorems like the pseudo-locality theorem. So basically, our strategy is we're going to pull back everything to the covering space. So we can pull back the universal covering. We can pull back the flow to the universal covering space. Suppose we let pi denote this covering map, and let this g tilde as the pullback of the flow. So instead of showing the uniform estimates for the Ricci flow down on the original manifold, we want to consider this covering flow. So basically speaking, in view of the pseudo-locality theorem and the distance distortion estimate, we need to show that the covering flow satisfies the local Euclidean condition. if that satisfies the condition for the current flow, I can estimate the existence type uniformly. And that that flow exists, and that's associated to the flow downstairs. So we're good. So therefore, our K lemma is to show that the Euclidean, show that the universal current space is almost Euclidean. So basically, given epsilon fixed, we have this delta ALE, not the usual ALE. Although it's still the almost Euclidean condition, it's not the usual ALE like with coordinates. So the delta ALE and RALE solely determined by this epsilon, n, and d, and v. So these are the parameters that we always use to the following fact. If M is in this larger moduli space and N is one of the minimum models such that these two manifolds are sufficiently close for the delta ALE, and we have the maximum first Betti number difference, then for any scale up to this uniform RALE and any point in the universal covering, we have this local Euclidean condition. The volume of the covering geodesic ball, volume of the geodesic ball in the covering space is almost equal to the n-dimensional Euclidean space. So that's our K lemma here. Any questions here? Okay. So how do we prove that theorem? How do we prove that lemma? We will base our proof on this so-called epsilon regularity theorem due to Neighbor and Zhang in 2018. Their theorem is for the Ricci curvature. So to state their result, let's first define some concepts. The so-called, let's define something called the pseudo-local fundamental group. So it is given any say point in a manifold, and for any delta, we look at the image of the fundamental group of the small ball included in the whole manifold. So basically speaking, this gamma tilde delta p is considering all the loops contained in the delta ball around p, and you allow them to deform within the whole manifold. You can have a small loop, non-trivial loop here, but maybe around somewhere else in the whole manifold, it's killed. So basically, you just consider this image. So basically, if we have this universal covering, then the restriction of this geodesic, so basically, if we have a covering space, normal covering space, and I can restrict this covering map to a geodesic ball downstairs, then it's a normal covering. And the deck transformation is, of course, the pi1 here, because we can consider this universal covering. And for this normal covering, we can consider the following group G hat delta P. So that's all the elements of the fundamental group such that its action on the base point of the universal covering is less than 2 delta. And with 30 seconds thoughts, we can see that they are the same group actually. Yeah, because one is considered a very short loop that can be deformed in the whole manifold. That's the same as considering the small enough actions on the universal covering. So they're the same group. So Neighbor and Zhang's result stays for this group, G delta hat. So this actually their theorem is in 2006. So this theorem says that for any epsilon, there's a delta such that if MPG is a point in Riemannian manifold with Ricci curvature bounded below, and let's say a technical condition, the radius 2 geodesic ball is compactly contained in the radius 4 geodesic ball, then for any normal covering, so here in our mind, the normal covering is the universal covering restricted to the geodesic ball B2, BP2. And then for any normal covering with, well, it's a pointed covering. If we have this, if this, not the covering, if the original geodesic ball is close, very, very close to the Euclidean, lower dimensional Euclidean K ball. Lower dimensional Euclidean 2 ball. K is the lower dimension. Then this G hat P is almost nilpotent with nilpotency rank not exceeding n minus K. Moreover, if this nilpotency rank is equal to this, n minus K here, a typo here, sorry. Moreover, its nilpotency rank is equal to n minus K, namely the maximum rank. Then it holds that this covering ball is Gromov-Hausdorff close to n-dimensional Euclidean space. If the lower ball, if the original ball is Gromov-Hausdorff close to k lower dimensional Euclidean space, and to put together with this condition on the rank of the local of this G hat, then this covering ball is very Gromov-Hausdorff close to this n-dimensional Euclidean space. That's their theorem. Yeah, here basically pi hat will be the restriction of this universal covering map to the pre-image of the geodesic ball. And in this case, we have, because as we said, G hat delta P is the same as gamma tilde delta P, we have this pseudo-local fundamental group has rank less than or equal to n minus k. And its equality gives that on the universal covering space, the geodesic ball is close to the Euclidean n ball. And then by many known results, we can conclude that suppose we get this condition, then the volume of this ball is very close to this n-dimensional space form, the volume of the n-dimensional space form times R to the n. Okay, but here the concept is that what is the almost nilpotent group? Well, we actually all know that, but what's the rank? Basically speaking, for any almost nilpotent group, we have a polycyclic decomposition, so that each of the steps is either cyclic or like finite or cyclic finite. And the rank is actually defined as the copy of these in this cyclic decomposition. And of course, classical algebra theorem tells that this is independent for specific polycyclic decomposition, the rank. Yeah. So in our setting, any like this cyclic, this Z copy in this gamma delta P actually counts a small circle around a small non-trivial, the small circle around base at P that is non-trivial in the whole manifold. Yeah, so any Z factor. So basically we can now understand Neighbor and John's theorem as saying that if this original manifold is very close to this k-dimensional Euclidean space, and if they're roughly speaking, they're n minus k loops, independent loops, then if you open that on top, locally you're gonna get m-dimensional Euclidean neighborhood. So that's how you understand that theorem. All right, so here we notice that, so the difficulty of applying their theorem to our case is that their theorem is, I'm getting its neighborhood, I'm getting this local rank, this local group, and I get rank. I get all the information very specific at the point. But then our assumption is just Betti numbers. Give me some Betti number, give me a point. I cannot tell what's the effect of the Betti number on the fundamental group, on the pseudo-local fundamental group of that point. So we need to connect this. We need to connect these two things. So that's one of our major input here. So basically, besides the pseudo-local fundamental group, that's one element that we introduced to connect these two concepts. We also, we also introduced the small homology groups. So basically, that's the integral homology groups. That's a subgroup of the integral first homology group, and that's generated by loops of length less than say epsilon. So that's an abelian subgroup, finally generated abelian subgroup of the first homology group. So basically, under the assumption that the Gromov-Hausdorff distance of M and N are sufficiently small, we have shown this. The difference of the first Betti number is equal to the rank. Here, the rank has no ambiguity because this is a finally generated abelian group. We can show that the difference of the rank of this small homology group, small first homology group. So basically speaking, this small loop, they can travel freely around the manifold.
So the 10 epsilon, I mean, could it have been just anything bigger than epsilon? And why is it 10?
So here, epsilon should be sufficiently small compared to certain constant determined by the properties of the moduli space of N.
Okay.
So because N has finite many topological types, right?
Mm-hmm.
Basically speaking, it says that at certain scale, say it's the scale mu, and the topology of N is trivial. Mm-hmm. This epsilon should be definitely much smaller than that I mean, that be smaller than that scale, say 1,000th of that
Okay.
scale. Yeah.
I
Only on those scales we can prove this thing.
yeah, but then why do you have length not exceeding 10 epsilon?
Why do I have? Actually, yeah, this is something like just for technical convenience. In the
No, I know, but I'm saying that 10 is not important, right? It could be anything bigger than 1. Is that or
right.
okay.
Like say 50 is good. 20
2,
is good.
2. Yeah. Okay.
Actually, sorry, 2 may not be good because I need to do some inequalities, but 10 is good enough.
Okay, I see. So you're just doing a finite number. Okay, I see. Okay.
Yeah. Yeah, I need to do some calculations. Eventually, I get to say like I need to make up to say like 9 epsilon.
Mhm.
If I have this condition, then I get all the estimates up to 9 epsilon or something like that. Yeah.
Okay.
Yeah. But here the point is that when epsilon goes to 0, these are all in the same. These are all comparable, uniformly comparable. So actually, part of our generalization is Coding and Neighbors. One of Coding and Neighbors' work in their annals paper, because we need to sort of compare if a circle anywhere in the. I mean, we want to compare a circle that defines one element here, that defines one rank here, to if I slide this circle to any given point, I need to compare the distance. We need to generalize the work of Coding and Neighbor in order to show this. See, this is like a localization. The rank of this thing is represented by circles scattering around the manifold. We don't know where these representatives are. But we can localize that thing. I can translate all those circles to any given point and say that actually I can compare those circles so that we can show this inequality. It actually took sort of 1/3 of our writings to prove this inequality. Yeah. So basically, we can locate any point. I can put this information to that point, and I can show that this rank does not exceed the rank of this almost nilpotent group, which by Neighbor and John's theorem does not exceed n minus k. That's why that's actually part of our theorem, saying that b1 minus m minus b1 n is less or equal to n minus k. Yeah. Therefore, if we have this equality, it forces this rank to be maximal. Therefore, by Neighbor-John's theorem, we can see that the universal covering of M is locally n-dimensional Euclidean space, resembles n-dimensional Euclidean space. And I can go back to apply the pseudo-locality, the distance distortion estimate, whatever, and then essentially eventually apply Fukai's theorem. Yeah, so that's how we prove it. Yeah, these are just technicalities. Maybe do I have time? I don't have much time. So as we said, we can from here we apply Neighbor-John's theorem to find locally Euclidean universal covering, and then I can use the pseudo-locality to estimate the flow existence time, distance distortion. Then after rescaling the metric, it's still sufficiently collapsed. After rescaling the evolved metric, which is smooth enough, which has uniform curvature bound, and is sufficiently collapsing, and therefore I can apply Fukai's fiber-bundle theorem. And basically that's it. However, Fukai's fiber-bundle theorem only tells that it's infranil fibers. We still need to check that it's torus, but that's not very hard as long as we can take advantage of this fiber-bundle structure. So basically, we know that because locally it's a fiber bundle, the pseudo-local fundamental group is actually the pi1 of the fiber, because locally it's like a fiber cross a trivial ball. Therefore, we have this. And therefore, by the Ricci theorem, we know that n minus k equals to the rank of the rank of this, and that is nothing but this local pseudo-local fundamental group divided by this commutator intersecting this group. And of course, it's rank because it's almost nilpotent. Therefore, and once you quotient something, you basically kill the rank. So that's the rank of the quotient is less or equal to the rank of this thing, and that's less than n minus k by Neighbor-John's work. So if the equality holds, it forces this thing to be trivial, because if this commutator is non-trivial, then this rank drops non-trivially. Therefore, this forces the almost impermanent group to be a finally generated abelian group. So therefore, each fiber has an abelian fundamental group, and therefore it has to be a quotient of the n minus k torus. But then, because it's a fiber bundle structure, if you have the fiber is actually a quotient, then since the total space is a manifold, it has to be the case that you have some action on the fiber, on the central fiber, and some action on the base that faces the central fiber. You have to have something like this. But in that situation, you're going to end up with a orbifold collapsing limit, not manifold. Therefore, it has to be the actual torus, not any final quotient of the torus. And therefore, that's the proof of the theorem. Yeah, I guess, yeah, I managed to finish before 1 hour ends. Yeah. Thanks.
Thanks very much. And any questions for Shaosai? So what does this now tell you about SYZ conjecture or abundance?
This does not tell us that conjecture.
No, I know, but does it help?
So basically, I would say that, let's go back to the theorem. Basically, I would say that this Betti number assumption is way very small here. Like in SYZ conjecture, everything is simply connected. So you don't have this assumption here. But I think the key ingredient here, besides the Ricci flow smoothing technique, the key ingredient here is what I said, this H1 inequality. This H1, the rank of H1 epsilon is less than or equal to n minus k.
Mm-hmm.
Sorry, that's not, I won't say this one. That's the generalization of coding and neighbors work. So what we were able to do is to, so it is this last inequality. I think that's the major input that might be useful for any collapsing for the study of any collapsing geometry. Because what we have here is, suppose I'm having a closed geodesic that represents one element that generates the rank. And I want to say that this closed geodesic, if I slide it along some geodesic that connects to another point, and I want to say that this closed geodesic, when you slide it to that point, I want to control the size of this thing. How do I control the size? Basically, what I do is, on the universal carrying, this closed geodesic, the length is approximated by, the length is measured by, what can I say? So basically, you have a closed geodesic here that represents one element here, one rank here, and you can slide along sigma to some point P. Mm-hmm. And I know that this loop gamma represents some elements in the local fundamental group in the fundamental group base at P. But what I want to estimate is the size. So what I do is this sigma you lift to the universal carrying. There's one is the sigma tilde, for instance, and there's another is the gamma sigma tilde. You take the action. So basically, what you have is two geodesics that goes to the preimage of P. And therefore, I want to compare the spreading of these two geodesics. So what you can do, what you can make use of is that, suppose you have a generic collapsing, say Calabi-Yau manifold or Ricci flat manifold. Mm-hmm. You can use that thing to compare say, for instance, I have one fiber, I have another fiber, I have some regularities of the fibers, and then I can compare the sizes of the fibers.
Right.
Because this distance, you have two geodesics going there. You compare the spreading of the geodesics, you can compare the distance here. And then you have sort of a comparison of the fibers. That's what I think is the major technical improvement here. And that's why I think it's going to be helpful in the study of collapsing geometry.
Right.
Yeah, but beyond these technical layers, we're going to have something very easy to present. That is the fiber bundle theorem that we just applied and get. Yeah, but in the future, I think what's the most useful is going to be this thing, like you can compare the spreading of two geodesics. So basically, Cody and Neighbor was able to compare the spreading of geodesics starting from a single point. But that's already very useful. That's an analysis paper and proves something very fundamental. But then if you have a submanifold, you have some geodesics perpendicularly emanating from that. And if you can compare this spreading of the geodesic, you can basically say, sort of like I translate this submanifold along this family of geodesics, then I can see the spreading of this manifold.
I see.
Yeah. So I think that's what's going to be useful in the future.
Any other questions? Okay, so before we thank Shaosai again, let me say there's another talk scheduled next week. It's Mark Haskins from Duke. And as far as I know, we don't have anything else currently booked for the rest of the term, but I think some of the other organizers are working on getting a couple more speakers. Anyway, so let's thank Shaosai again.
Thank you.
All right, thanks very much.
Bye.
Bye, everyone.